Hello, everybody. Welcome to this webinar about composite beam design. It's a special webinar because, Ricardo, can you maybe mute your sound or put the sound in some ears because I hear myself back in your microphone. Yeah, thank you. This is a special webinar because we are joining forces together with Ricardo Zanon from Arcelor Mittal. And we are sharing the topic today about composite beam design. First, Ricardo will give you some overview about composite beam design, the possibilities and technicalities, and introduce you to some case study that I will then later build up in SCIA Engineer and show you all the details about how you can model and check these structures in SCIA Engineer. Okay, I hope you can all hear me fine. Normally you guys are muted during the webinar, so yeah, you won't be able to talk. But if you have any questions, you should be able to locate a box with a question mark and post your questions in there. And then we can look at those and try to handle them maybe at the end of the webinar. And with that, I will pass the word first to Ricardo for his part of this webinar.
Thank you, Yael. So I will start my presentation. Please, if there is any technical problems in terms of sound or in terms of visualization, please, Yael, stop me. So welcome also from our side. So as ArcelorMittal here in Luxembourg, we are a user of SCIA Engineer, so from the Nemecek product since over 15 years. And over the last years, we have started a very proficient, I would say, collaboration. Also from the scientific point of view, we try to share our thoughts, our issues, and to solve them together. So I'm very happy. Thank you, Yael, for inviting us. It is the second time that we make this such a webinar together, and it's a pleasure. So basically, the idea is that we from ArcelorMittal, we share what are the practical applications we have been working on, and in fact, Yael will show how this can be handled with the software SCIA Engineer, which is the software that we basically use in our daily calculations. So having said that, let's go to the topic. So today we wanted to take a simple example of a steel concrete composite beam, which is in fact something which is covered by Eurocode 4, but I would say there are not so many design softwares which can handle it properly, and that's why SIA does it. So that's why we wanted to show this today. So very briefly, I am in fact a structural engineer. I've been working over the last very soon 20 years, mostly with steel concrete composite structures for buildings and bridges. And I am now, I have the honor to be part of some working group on the Eurocode 4. So I would say I am quite passionate and quite convinced about steel concrete composite structure. So it's really a pleasure to present this topic today. So I would rather start with a very short introduction. So what is a steel concrete composite beam? Basically, it is a structural element which is composed by two components, steel and concrete, and they work together compositely. That means there is an interaction between the two materials, and they act together so to make a composite section. The collaboration of the two materials is a key concept, and in some case it is necessary to ensure it by a specific element, which is the shear connection. The first realization goes back to the end of the 19th century. This is on the left. It is the bridge which is meant to be the first composite bridge, which is in fact a bridge where the steel beams are completely encased into the concrete. And the other one is Pullman-Decke, which is from Germany. It was a patent quite known in the literature, which also foresee a encased steel beam, but with specific connectors to ensure the collaboration between the two materials. But having said that, I would say the composite structure really took off when it was started to have downstand beams. So basically, usually you had the steel structures and a composite plate on top of it. And the idea which came was to make the two elements collaborating. So you can see, I would say, a schematic picture on the left. So instead of the two elements acting independently, one and the other, to take the loads, to then to tie them and to make them act together. So this was where I would say really the composite structure took off. You see one of the which is considered one of the first composite bridge to be calculated as composite, which is the Arcelor bridge in Lucerne in the starting of the 20th century. So in terms of codes, the first code was probably the New York Building Code in 1930 to really formalize this kind of structure. So as in the picture before, as you can understand, the key concept is basically to tie these two elements, which are, I would say, or ideally in a horizontal plane, and they have to act together via the interface. This interface, it is where the shear connection takes place. So basically, if you have no shear connection, it is the non-composite behavior, which is on the left. Basically, there is a gap in the strain, so there is, I would say, a connection between the two material. Whereas if you connect them perfectly together, then the stress continuity is continuous. There is a Bernoulli beam, so this is the case of a full shear connection, and basically the two materials act together. Why we do this? Because of course, as you can understand, we are making additional effort to tie them. Well, basically because the resistance of the stiffness of the beam is greatly enhanced. Here I take an example of Poreneco TDs in 2011, which I had the chance to work on. And I take, for example, the edge beam, which was a HL 1100 M beam. And basically just to show, by attach the composite slab, which was 25 centimeter thick, to the beam, we can achieve an increase of the composite of the stacking bending resistance of 51%, and an increase of the stiffness of more than 2. So basically an increase of 152%, which means the stiffness is multiplied by 2.5. So as you can understand, for a bridge or for a beam which has a decent span, this is something which is really interesting because you increase the resistance and even more the stiffness. So this is why composite structures have become very, very popular in the last century, I would say. So after this historic introduction, I would say let's look at the topic of today. So today we'll discuss about beams for buildings. So basically it is the Eurocode 4.11. And I take an excerpt of the second generation of Eurocode, and here you see a figure where there are the typical composite cross sections. We will talk we'll talk only today about the beams on the left. So basically a steel beam with a reinforced concrete plate on top of it, and you can have the steel sheeting, which is an option to create the composite slab. You can also have a full concrete plate, but I would say both are, I would say, typically composite downstream beam, but today we will have an option with a steel sheeting. So one word about the steel component. So basically here, as you have seen, typically we talk about double T sections. And I would say, to make it simple, there are mostly two main families. One, it is the hot rolled section. So basically it is an industrial product which is rolled to the final dimensions directly at the rolling mill. We have different families, and the tallest one goes up to more or less 1.1 meter. The other option is, of course, to make the double thick section out of welded plate. So basically, they are flat plates which are cut into different pieces, and these pieces, they are assembled together by means of welding. So it is typically a continuous longitudinal weld which make out a double T section. In this case, of course, you have basically no restriction in terms of geometry. You can tailor-made the geometry as you want, but of course, I would say it is a product which needs a bit more of manufacturing. We will not talk today about web openings, but just to mention that this is one of the big advantage of composite beams and steel beams, is that you can have a lot of web openings. Of course, sometimes you have to reinforce them if the opening is very big. But I think an important message is that basically you can insert the installation within the depth of the beam by making these web openings, and in particular for office building or some other buildings where a lot of MAP are present, this is a very interesting option. Just to mention that basically the steel beam with web openings can be done by just cutting of a full depth beam, or there is also the possibility to have the so-called castellated beams, which is, I would say, a higher engineering solution, where basically you have a double T section and you cut it out and you reassemble at a higher height. In this way, the cut, I would say, the surface which is cut off, it is not a waste, but basically you can achieve a higher inertia by using a smaller beam. Of course, in this case, you have some restrictions in terms of geometry, and the holes are regular. And you have the rewelding, of course, of the two parts. So, what about now the other component, which is the concrete plate on top of it? I would say there is, of course, the possibility to make a in situ concrete and on a formwork. This, I must say, it is not very common for composite structures, because basically when you make composite structures or steel structures, you try to be prefabricated and to go fast. So the two most common options are the steel sheetings, which is the picture on the left. So basically it is a corrugated sheet which is placed between the beams, and you cast the concrete on top of it. And or the other way is to use prefabricated concrete planks. Both options are possible. Today we will talk more about the steel sheeting option, which is in fact also a composite slab, which is covered by Eurocode 4, and is from the structural point of view very performant, because it permits to have lower thicknesses and lower weights. So it is, I would say, the perfect marriage between the composite slab and the composite beam. There are several types of sheeting. So basically, re-entrant steel decking, trapezoidal steel decking, deep steel decking, or special or other type of special systems. Here I put the reference from Arcelor Mittal, but I must say that on the market there are several products, and I would say you can use composite beams also with other products. To mention that to have a design, we as Arcelor Mittal offer a quite detailed design software which is called COFRA 5, and I put the link there in case you want to have a detailed design of this kind of systems. This is the solution with a composite, with a deep steel decking. Typically, we will not talk it today. We'll talk today about the traditional steel decking, which is placed on top of the beam. But you have also the opportunity to have this deep steel decking. In this case, it is typically 220 millimeter height, and then it is placed in the height of the beam. I just mentioned it. And the other type of steel decking is basically the flat one, where you can, as you can see, it is placed basically on top of the steel beam. This is quite interesting because the rock wool is automatically prefabricated in the depth of the steel decking. So basically, you have a floor which has already a thermal and sound insulation, which is quite integrated in the deck panel. There are other type of composite beams, for example, beams with concrete encasement. This is typically used for fire safety reason, because of course this concrete encasement ensure a very high fire resistance. And there is also the possibility to integrate the steel beam within the depth of the slab. So these are options which will not be discussed today, but with Yael we plan to do in the future other webinars. So maybe these will be the topics that we will cover in the future. And now, sorry, I will make a small. Sorry, but winter has come here in Luxembourg, and I've been one of the first victims. So now we come to the, would say, the topic of today. In fact, we will discuss about an example of a conventional downside beam. So basically, it is a steel beam with the steel sheeting and a concrete plate on top of it. In that case, in terms of installation, you can see the most simple and typical one is the one on the right. Basically, you have the steel sheeting, which is perpendicularly to the main beams, secondary beams, and then you can have primary beams which connect the columns and bring the load from the secondary beams to the primary beams. So this is typically the typical layout of a composite deck with composite slab and composite beams, with primary and secondary beams. What about the constructive detailing? In fact, the most common way to ensure the shear connection is to place headed studs. Headed studs, they are basically cylinders with bigger heads that ensure the collaboration between the two materials. It is an industrial product which is in fact welded on top of the beam, and it is been used since 50 years, and today it is in fact very common and very known, and also I would say quite economic way to ensure the shear connection. There are basically three options when you use steel sheetings. The first one is to interrupt the sheeting on the beam. So in that case, there is not really an interaction between the steel sheeting and the studs in terms of geometrical layout. The second of this first option, of course, in that case, the steel sheetings are isostatics, so it is not the best option in terms of composite slabs. The better option in terms of structural performance is when you have pre-holes steel sheeting. So basically, there is a steel sheeting which comes with some holes, and then basically you fit it with the shear studs that then stands out, and then basically you have a steel sheeting which is continuous, and you have the place for the shear studs. The other option to have a continuous shear studs, the continuous steel sheeting, is to weld the studs on the job site through the steel sheeting on the steel beam. So this third option, I must say, it is not very common in continental Europe. It is more common in UK and eventually in the US. But I would say I've not seen many construction sites in continental Europe using this third option. Of course, when done properly, it is very effective. And is also very, from the structural point of view and also from the tolerance point of view. But I would say in practice it is maybe less used than the two other ones. And here you can see basically the typical fixing of the shear stud, which is done mostly in the workshop. So this simple shear stud has a very, in fact, ideal behavior in the sense that it has a behavior which is can be associated to a rigid plastic behavior. So basically, you have first the elastic branch, and then you have a yielding, and then the behavior of this stud is ductile in the sense that you can achieve a significant slip, a significant displacement before coming to rupture. To achieve this, you have to comply with some simple rules, geometrical rules, which is basically the geometric aspect ratio, the 8 to the diameter. This is Eurocode 4, and in fact, it is basically what we use in everyday life. So basically, shear studs which are at least 4 times higher than the diameter, and diameters which are between 60 and 25 millimeters. When it comes to ductile, this is the behavior of one connector, but what happens if I have a row of shear connectors? The idea is basically that you have the steel beam below and the concrete plate on top, and you have at the beginning for low loads, in fact, you have a longitudinal shear connection which is acting elastically. So basically, you have a double triangular longitudinal shear. The longitudinal shear is, I would say, as a shape which is close to the one of the vertical shear, and in fact, you have all the loads on the studs which are also in the elastic range. When we start increasing the loads, what happens is that basically for example, shear connector D, which is close to the support, will start to plastify, will enter into the plastification, and then we will have a redistribution of the longitudinal shear towards the center. And at the end of the loads, basically, when we can arrive to the case where all the shear connectors are plastified, which is the picture on the right, where basically we have a quite homogeneous longitudinal shear, which is overtaken by all the studs. This is the principle of the ductile shear connectors, and that's why in buildings we like a lot to have this kind of ductile shear connectors, because it permits to have a uniform distribution of the shear connectors, and all of them are subjected to the maximal load. So in that sense, there is a maximization of the use of all the elements. to mention that this is the theory which is done in buildings. In bridges, we cannot rely on this, but in buildings, this is the uh, typical standard composite beams that we design. So now, after this introduction, I would like to talk about the case study that, in fact, we propose. I will describe, in fact, basically the building very briefly and the beam that we have taken out of it. And Yael will show you how to do this with SCIA Engineer. So the buildings that we have chosen, here it is in fact the headquarters of Cargolux in Luxembourg. It is a quite iconic building. There is in fact an article here. You will have the link, and you will receive the slide deck. So eventually you can look at the more details at the building. So it is a very nice building. Uh, I must mention that we will not talk about the building itself, which is also very interesting, and part of it is also with composite structures. We have decided to take a look at the car park, which is a more regular structure, where it is easier, I would say, to take off a standard beam. So the car park, as you can see, it is the building on the left, and basically it is a rectangular structures. Here you have all the companies which have been involved into it, the design office and the execution companies. We have the chance to supply the material. And in fact, it is basically a building with a rectangular basis where you have two ramps on the four ramps on the left, on the right side, and in the center we have a quite regular frames. Basically, it is the beams are pinned, so it is not a moment resisting frame. It is a pinned frames with the elements which are braced by the concrete cores or by the bracings. We will talk about a typical frame. Here you can see the central part, which is quite regular. So basically we have, as we have discussed before, steel beams, steel sheeting on top of it, pre-holed, and then you have the concrete flooring, which is done, of course, on site. We will take out a typical floor beam, which is in fact was designed as a IP400 in S460. The span, the theoretical span between the two axes of the column is 16.505 meters, and the beam interaxis is 2.5. All the beams are connected to the columns. In this case, we have also the columns with the same spacing as the beams. The shield connectors is a diameter 19 with a 8 of 100 millimeters with a spacing of 207. Why 207? Because 207 is the spacing of the ribs of the steel decking. The steel decking was a copper plus 60 with a thickness of 0.75, which carries on 2.5 meters, which is of course the beam interaxis. The total height of the slab is 150 millimeters, which is composed by 58 millimeters, which is the steel sheeting, plus a full deck of 62 millimeters, which is on top of the ribs of the steel deck. And here you will see the loads, basically self weights, the additional permanent loads, and the exploitation loads. So to mention that to make a pre-design of such structures, you can also use one of our pre-design software. You will find them on our website. So if you just Google it, basically, you say composite solution Arcelor Mittal beam calculator, and here you will see that you will find a page where there are several design softwares, and there are also some for composite solutions. Basically, there is one which is dedicated to beam and integrated floor beams, and one which is dedicated on columns. The current version you will download it, but in fact I will show you today also some print screen of the new release. In fact, it will be released next year, which is in fact a new generation of ArcelorMittal Build Calculator software. So basically, for what we will do today, the results are exactly the same, but I will just show you this because there is a bit more of I would say of colors. The layout is a bit nicer, but in terms of calculations is doing exactly the same. And it was also for me a good occasion to test it. So basically, well, I will not go into the whole details, but these are the inputs that Yael will show you how to input in SCIA Engineer. So basically, we will study then in detail a isolated beam where you have a spacing of 2.5 meters, and here you have basically the span, which is 16.505 meter, and the composite slabs, which I already described to you. So basically, you have to input the different parameters in whatever software you use. So basically, concrete class, the diameters of the studs, the geometric parameters, if the sheeting is pre-hauled, is interrupted, or is eventually through deck welding. So these are different options that I explained you before. The arrangement of the studs. These are all the parameters which are taken into account in the verification. One important point, which is in fact you can do it by many ways, is not to forget, in particular, is to verify the stability of the structures during the concreting phase, because in most of the cases these beams are not propped. This is also one of the main advantage of the composite construction, that basically you can avoid prop it, but actually the final resistance of the structures is the same, so you don't lose any resistance by not propping. So this is why basically composite structures is often not propped. In ABC, we have the possibility to make a verification by considering the steel decking, but of course, another option is to put temporary bracing, which is also quite used to, in fact, to ensure the stability of the beams. And then you have a calculation report. I will not go into it because Yael will show you how it is done. And we checked, in fact, over the last days, and the results are quite the same using these simple pre-design tools, or I would say the full design tool, which is SCIA Engineer, which of course permits you to design the whole building and then eventually make the focus on a specific element. So, by having said that, I thank you for your attention. I hope that this introduction was useful for the composite beams. And now I leave the floor to Yael, which will make you a demo of how you can do it in real life with the design software. If there are any questions you can of course write me a mail or eventually write in the chat. I will be very happy to try to answer them.
Thank you, Ricardo. I checked the questions, and so far the only question is to share your presentation with us. I think normally you can do it in this platform. There's a tab where you can add attachments, but if it doesn't go, then I will send it to the people afterwards. Yeah, so thank you for this interesting part, and now it's on to me to show you the SCIA Engineer side. My bottom neighbors have decided that this is the ideal moment to make renovations to their apartment, so I hope the sound is not coming towards you guys. I will try to stay focused on my end. So I'm Yael Verkammer. I work at SCIA now already 9 years. I've started at customer support, where I was answering questions from our users and also giving trainings. So I also gave a training to Ricardo once, some many years ago. And now I am in the product management team, where I'm responsible for the new developments for next versions, what to implement, how should it be implemented in SCIA Engineer to be the best they can be for our users. And here I'm responsible for all that is material design. So yeah, Composite is definitely one of those. Now I will share my screen. And for today, I have not prepared any kind of PowerPoint or presentation. I have just prepared to live build up this model into SCIA Engineer and hopefully come to the same results as Ricardo had. But if not, I will probably just have made a modeling mistake. I have another model prepared that I already built yesterday. But normally we should be able to get there. So I will just start a brand new project and show you SCIA Engineer, how it works, what to do. So for this case, composites, of course, we need both concrete and steel materials in our project. I will change here the default material to 460M, which is the one used for our composite beams in this case. The rest I can leave like this. I can ask this one composite beam hub. In terms of functionality, there's nothing specific we need to set, so we can just start up this project and yeah, start modeling. The first thing I will add is some columns. Let's add in the proper cross-section that we need, which for the columns in this case was HEA 220. Okay, I'll use this one, and they are 2580 length. Okay, and then to place them down in my model, I will just type the coordinates. If you put 0, it will straight away put it in the 0, 0, 0 point, and the next one will put it 0 and then 16.585 meters. There we go. Yeah, so that's our first part of the model. Next, let's add the composite beam. IPE 400 there. Let's add this one in. Okay. So here I chose the member option. There's also a beam option where I give the length width. But here, since I placed my columns already at the proper length, with the member option, I can just select the 2 nodes and the beam will be of the proper length. And then let's make some height to this building. With our multi-copy tool, I will make 3 copies. And I will just use the cursor to define the distance, because the distance is just from the bottom to the top of the column. There we go. And then finally, I will select I want to select actually all of my members, but without selecting the nodes. So for this, I will select just one beam. And then anything that's the same for all my elements, like for example, I've not inputted any eccentricity, I will expand the selection. So there we go. And I will add these 2 nodes into my selection. This is because I want to make again, a multi-copy, but I want to link the top nodes with some beam just to have some sideways stiffness in this model at the top level, because there will not be a composite deck on the top floor. So, and then I want to repeat the last command I did, which I can just do by pressing the enter button, and I'm straight back to the multi-copy menu. Here I will make 4 copies. I will select this one, so connect the selected nodes with new beams, which is why I selected the top nodes. And this time I will input the length. I think we are at 2.5 meters in between each of the beams. Yeah, that's correct. And I press OK. And then here I can select some kind of other profile for the top. It doesn't really matter. And here we go. We have created some kind of first structure quite quickly. To finish it off, I will put some supports. There we go. And yeah, that's a very quick way to set up this model. There's other ways you could go quite as quickly as I just did. That's by using the predefined blocks, the catalog blocks. Yeah, these ones. Where actually you can also quickly set up 3D frames and define the lengths of everything, how many repetitions you want in each direction, and the cross sections to use. But yeah, I myself generally tend to forget that option and just straight away model it. Okay, so now we enter into the more composite specific kind of modeling, because we will need to define a composite deck. So I will generally with the new UI, I just type in the top, what am I looking for? And straight away it's there. That's how I use modeling most of the time, but there's many different ways you could use the new UI. Yeah, so let's see. We need the Cofra plus 6075. That's the one. So as you can see, we have a big database of different sheetings available. If yours isn't in there, it's also possible to create a new one and put your own characteristics in there. But of course, yeah, that's a bit more work. Luckily, quite a lot of them are built in. So here I have this one. Yeah, so that's my composite deck with the sheeting that I chose. I can then set the concrete material and the thickness. I think those are the most important to get the proper results. And then I can just go ahead and input them. I select just the nodes for the member, and there we go. Okay, once I input a composite deck, SCIA Engineer will inform me that he is going to create some load cases. So SCIA actually automatically creates self-weight load cases for all projects. But for composite projects, it's a bit different because he's creating also some different load cases for fresh concrete and dry concrete, which are fresh concrete is taken into account into the construction stage checks, and then the dry concrete is taken into account into the final stage checks. So yeah, so he's just warning us about creating these items, and then I will copy my deck up to the other two levels. And then I think very important for your composite decks is to check the orientation once you've inputted them. So as you can see here, I have the arrow pointing with the beams and also the sheeting placed in the direction of the beams. That would be quite a bad way to design this structure. Of course, you want the composite deck to be carrying perpendicularly to our to our beams. So I will just select these, and I will change the angle of the local axis by 90 degrees. So I can do it here. There we go. And here you see that the angle has shifted into the proper direction. You also see some extra lines appear. This is for the redistribution of the loads. So here in my element behavior, there are different ways in SCIA Engineer you can choose to take into account the composite deck. Either you can use its stiffness through a standard finite element method. So you will just have a plate that will distribute loads as is expected from just a finite element deck. It will have stiffness for bending, for shear, for everything. But it will lead to some non-equal distribution of the loads. You will have some extra loads arrive in the middle, and on the sides, the deck will actually load off some of its loads to the columns, for example, rather than to the beams first. And this will bring you to some quite different results than you generally anticipate. And this is why the other options are there. So you can choose to calculate with a flexible diagram, which will have also no shear stiffness and no bending stiffness, and the loads will just be equally divided for, well, each an area for each beam is assigned, and whichever load comes to its area will be assigned to the beam. You can have the rigid diaphragms, which will have actually an in-plane stiffness, so that you can get some in-plane stiffness in your model taken from the composite deck. Or you can have a semi-rigid diaphragm, where we will account for the actual shear stiffness of this composite deck, but not for the bending stiffness, so that the loads are still properly divided along the beams, but the actual stiffness is used for the shear stability of your element. If you forget all of this, I can highly recommend you. I will also share the link here in the chat later. There is a 168 pages long book about how composite design works. And here, for every type of diaphragm, it explains you which kind of stiffness is there and isn't there, and what behavior to expect from each of them. For now, I will go just with the rigid diaphragm option, because we're not really going to consider the shear stiffness of this model either way. Okay, so very, very important to know and often quite forgotten by first-time users or surprised is that at this point in time for SCIA, the beams and the composite deck are not yet combined together and considered as a composite beam for the design. So to consider that these beams are actually linked to the composite deck and they are working together as some composite beam unit, we need to connect these members as ribs. This also allows you to have some beams under your composite deck that don't have shear studs and are not connected, and to still calculate these and not automatically have them considered as composite beams, right? So yeah, first thing, important thing to do is to connect members and nodes. Yeah. Yes, I want to do it for all, and I will connect the 1D members as ribs. So this point, very important. Okay. What you now see is that some more lines have been added into my model. So our ribs have been connected, and the extra things you see is actually the effective width that gets calculated by automatically by SCIA Engineer according to the Eurocode. He will calculate how wide this width is. Now, currently, it doesn't look logic at all. That is because first, calculation is required to properly calculate this effective width. So if I just run a quick calculation, yeah, I need to have more mesh elements divisions, but luckily SCIA reminds me and does it automatically. Dum, 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 dum. There we go. So now you will see that the effective widths are more logical. This one gets this half. The ones in the middle get the two sides of them. If there was more spacing in between, maybe the effective widths wouldn't be touching each other, but in this case, they are. So I guess the full composite deck is being used here. Yeah. And also, final points to mention here is once a member is connected at a rib to a composite deck, you will find an extra option here, which is called type of connection, where you can choose with standard composite action, without composite action, or user-defined eccentricity. So this is actually to care about the location of these beams, because as you can see in my model, the beams are overlapping with the slab. Like the slab composite deck is arriving in the middle of the beam. And in reality, the beam will, of course, be sitting under the composite deck. But for the analysis, if you are here working with standard composite action, you shouldn't touch the eccentricity of the beams at all. In the analysis behind, so in the calculation, when SCIA does the calculation, and we have defined some composite deck with beams that are linked as ribs, he will automatically put the eccentricity of both the slab and the beam such that the neutral axis will be the middle of the height of this slab and where the beam is defined. So in the calculation, he will actually move this slab up for his stiffness calculation and move the beam down for the stiffness calculation to get the normal neutral axis. And also, if you then do a design at the end, the check for the composite beam, you will do the check of the composite beam with the neutral axis at the correct location that he will calculate himself. If you are not comfortable with this, or you don't want to use the composite check and you want to define it yourself, then you can go for the user defined eccentricity and input your eccentricity yourself, but then the checks will have forces that are not correct in them, so you cannot use those. And without composite action speaks for itself, where the beams and the composite deck will not be collaborating. I'm checking that I said everything I need to. Oh yeah, so if you don't like the fact that these beams are sitting in the middle of the slab for your pictures, you can always use the structural model in SCIA Engineer and give the eccentricity for the structural model so that in your pictures the beams are at the proper location, but then for the calculation also you haven't moved them and they will still run smoothly. And final thing to do is again I will expand my selection to get all my composite beams, and I will add some hinges on both sides. Okay. Then let's move on to the load cases. I already talked a little bit about load cases, telling you that SCIA automatically generates the self-weight load case and the fresh and dry concrete. As you can see, the fresh concrete is in the construction stage. The dry concrete should be considered in the final stage, but yeah, we will see it in the end that it's properly taken into account. I will write it down and see what the issue is coming from. In any case, if you add new load cases, you will be able for the composite analysis model to define in which case the loads should be considered. Here I will add some permanent loads to the construction stage. And let's change this one also. And some variable loads for the final. These are not permanent but variable. We also change this to variable, and this one indeed final stage short term. They're not construction loads. They're just, I guess, the loads from the cars that are parked in our parking. Guys, I like to give everything logical names because then if anybody else is checking my models, or then they know what everything was about. Yeah, there we go. So my load cases are created. This is the variable load case. I will add in here a surface load on a 2D number of minus 2.5. Okay. On all of my slabs. And then I will add the permanent load case. Again, I press enter because I repeat the same command of adding a surface load to all of my slabs. Okay. And there we go. And then when I calculate this, so you see now I put this load on the composite deck. If I calculate, you will see, we already saw it blink a little bit before the calculation window opened. But the loads get distributed to the beams, and it's done in some predictable linear fashion, right? Here, 1.25, so actually this distance, because this is 2.5 meters, so half of it is 125 goes on this one, and this one gets the 1.25 from each side assigned to him, so 2.5. This is because we have this load panel kind of behavior of the slab where the load is just equally distributed towards the beams, so kind of matching better the hand calculations than if we take a finite element type behavior where the loads would be distributed a bit more unevenly. Yeah, so that's the loads. Let's just have a quick look also at combinations. So if you have a composite deck in your project, not only do the self-weight load cases get generated automatically, but also the combinations get generated automatically. So we have a ULS combination for the construction stage, an SLS one for the construction stage, then one ULS for the final stage, one SLS for the final stage, and the accidental load. And here you can see that for the final stages, we have the dry concrete, and for the construction stages, we have the fresh concrete weight, right? So then it does happen properly, and just that the little text was wrong there. Okay, so we have our combinations, we have our loads, we have our structure. It seems like we are all set for going to look at results in the composite beam design. So composite design, you will find it in your wheel. here at the bottom. If you don't find the composite option, which looks like this, you can open here in the hamburger menu. You can always remove things you don't need, add things you would like to see. And there is the composite one. So make sure this one is activated, and then you'll be able to find it in your menu. So I'm going here for composite, and I will first have a look at our composite design settings. Okay. So first off, we can choose to yes or no take creep into account, change creep coefficients, say if the beams are propped or not. In this case, they were unpropped, as Ricardo told us. And then important here is that there are multiple approaches for a composite beam to work. So there's two ways to work with composite beam design in SCIA Engineer. Either you go for a design where actually SCIA Engineer will propose to you which kind of beams to use, what's the layout, etc., based on what you want to achieve. And this is chosen here. So you can choose your design approach. You want to either minimize the size of the beam. That's by going for 100% connection or 100% connection for the composite action. Or you want to minimize the number of studs, or you want to do something balanced in between both. Or if you go for user defined, then you can yourself set which degree of composite action you want to aim for, and then SCIA will design the beams and the studs in accordance to this. But in this case, we already have a beam size and a stud layout, so we just want to check if they are correct. In this case, I set the calculation approach to check. When I do this, it becomes possible for me to change the degree of composite action because this is the number that is used in the calculation for obtaining results. For obtaining the stiffness and therefore obtaining the deflection results and the moments in this case. So I know in this case that our composite action is around 81%, so I will set here 81%. If you don't know yet, you could run the design, have your beams ready, look at the output of the composite action, then input it here and rerun the calculation to verify if everything is still okay. So in this case, I will set it here. Final important thing to change here, I guess, is which studs we are using. So this one has a diameter of 19, and we use the 355 material. Okay. And what was the spacing? Every 207 meters. I have one connector per row, so that is correct. Okay. That's all for the settings for now. So let's have a look. Oh, yeah. As I said, when you change the degree of composite action, it changes the behavior of the calculation and the stiffness. So since I changed it, I lost my results, right? Because we have a different stiffness of the slab. So I will need to recalculate the project again. Luckily, it's not very big, so it goes quite fast. And we get to look at our new solver dialog as well. Okay, there we are. So let me maybe select a specific beam also to look at the results for. And there we go. So we have our composite beam ULS plus SLS check. Let's go for, for classes. This is another thing that's automatically created, is a class composite design, which contains all of the combinations that we have for checking the composite. So the SLS for the final stage is in there, for the construction stage, and the ULS are all in there. And for the output, I would like to look at the standard outputs. So let's refresh and look at the results. There we go. So according to SCIA, our beam is failing. Let's open the report and look at what's going on. So here we have the summary of our input data, of our geometry, the beam properties, the slab properties, and then we have the summary of the checks for each stage. So Here, the construction stage, everything seems to be going just fine. For SLS construction stage, we have some issues with the deflection, but I think this comes because we are limiting our camber alignment to maximum 100 millimeters. So we can also go change that in the settings to allow bigger camber settings. And maybe also in car parks, we can allow a little bit more deflection. I'm not sure. For ULS, you will see that we get approximately the same results as the software Ricardo showed you from Arcelor. And everything passes. And then finally, again, for SLS here, we have some issues because the camber is limited to 100. I think if we increase, it should be passing just about. And finally, we have an issue with the natural frequency, but it's because we are saying that it cannot be under 4 hertz, but this is again a limit for buildings and not really applicable for car parks. So we could lower this limit and then the check should pass. And then finally, we also do detailing checks where we check if the concrete cover is okay, the thickness of the steel sheeting, the height of the studs, the distance from the edge of the flange to the studs, etc. All of these are okay except the minimum concrete cover of the connectors. I think maybe I could adapt the exposure class of the concrete, and then this check will also be fine. It's something that I didn't look into earlier in the settings. Or you can also choose to ignore this check. For example, we can consider that actually on top of our concrete slab, there is still a thick layer of the road that the cars will drive over, and therefore the concrete cover will be fine. I can also in the settings choose to deactivate this check. And then finally, in the design summary, you see that we have calculated the shear connection value, which is here at 82%, which is very similar to 81. So no need to rerun the calculation with the new value. The results in the end should be quite similar. Yeah. If you want more details or less details, you can open the brief and the detailed output. In the detailed output, you will really find all of the details on how the calculation is done and how every single value is obtained in those unity checks. So you can see the full formulas, the references to the codes, everything filled in. So there should be no surprises or no value that you can't figure out where it is coming from and why it is different. And that's also what made it easy to compare the SCIA results to the results from the Arcelor Mittal tool. And I think I have reached the end of the allotted time we had for this webinar by now.